In this section, we're going to look at current and resistance. Current and resistance. So let's start by defining current. Current is basically rate of flow of charge. Rate of flow of charge. So let's say we have this wire, okay? And let's say it's a cross-sectional area. If a charge Q crosses this cross-sectional area at a time interval delta t, okay? The rate of flow of charge, which is charge, divided by the time taken, is what you call the current. So you can say this is amount of charge that crosses a cross-sectional area of a wire per unit time. Okay, per a unit time. So if a charge Q crosses this cross-sectional area in time interval delta t, we can define current to be the charge divided by delta t. Okay, that'll give us the average current. So in this formula, I stands for current, Q stands for charge that crosses a cross-section in a time interval delta t. Okay, so basically current is rate of flow of charge. Now let's look at the unit of current. This unit of I. Okay, as you can see from this formula, it's the unit of charge divided by the unit of time, that is coulomb divided by second. Okay, that's defined to be ampere and abbreviated by capital A. Okay, so let's look at an example. Suppose, let's say, a charge of 2 microcoulomb crosses the cross-section of a wire, let's say in 2 milliseconds. The question is, calculate the current. Okay, so we have a certain wire over here. Okay, this is a cross section over there. We're saying this charge 2 times 10 to the power negative 6 coulomb crosses this in a time interval that is 2 milliseconds, or 2 times 10 to the power of negative 3 seconds. So, and we're trying to calculate the current, question mark. Okay, so current is charge divided by time taken. All right, so the charge that's crossing the cross section is 2 times 10 to the power of negative 6, and then we have the time taken, which is 2 times 10 to the power of negative 3, and this gives us 1 times 10 to the power of negative 3 amps, or which is 1 milliamp. Okay, so the next section we're going to look at resistance. So we're going to start by defining a resistor. A resistor is a device that converts electrical energy to non-electrical energy. For example, this could be a heater, which converts electrical energy to heat energy. It could be a light bulb, which converts electrical energy to light energy. It could be a speaker, which converts electrical energy to sound energy, and so on. So a resistor this is a device that converts electrical energy to non-electrical energy. Okay, so examples, it could be a heater. This converts electrical to heat energy. Okay, it could be a light bulb. It converts electrical to light, electrical energy to light energy, and so on. Okay, you can have a speaker that converts electrical energy to sound energy, and so on. Okay. Now the circuit symbol of a resistor. In a circuit is a zigzag line like this. This is the circuit symbol of a resistor. All right. Now, when you connect a resistor to a source of potential difference, such as a battery, of course, charges will flow. Okay. So first, let me set symbol of a battery or a source of potential difference. Circuit symbol of a battery or a DC source, as we can see in the later chapter, is this symbol: one short line, one long line. The short line is negative terminal, the long line is positive terminal. Okay, so suppose a resistor is connected to a source of potential difference, such as a battery. Okay, so we have the following circuit. You have this battery, source of potential difference, connected to a resistor. It could be a lamp, it could be a heater, and so on. Okay, suppose this source of potential difference is providing a potential difference delta V. Okay, so what's going to happen is this positive terminal over here is going to attract electrons from here. Okay, so this negative terminal repels electrons. This one repels the electrons, this one attracts the electrons, so we're going to have flow of electrons this way. But even though charge is carried by electrons, conventionally we assume charge is carried by positive charges. Okay, so conventionally we assume current is carried by positive charges. So positive charges will go this way. They're repelled by the positive terminal over here and attracted by this way. So the direction of the current, which is the direction of positive charges, will be this way. So this flow of current through this conducting wire is what we call current. Okay, so this is current. All right, now we're looking at the relationship between the potential difference and the current crossing this device over here that we call a resistor. Okay, now experiment shows that this potential difference is proportional to the current. That is, if you double the potential difference, the current will double. If you triple the potential difference, the current will triple, and so on. Okay, so experiment shows that the potential difference is proportional to the current, and that relationship is called Ohm's law. Okay, so let's state Ohm's law. Ohm's law states that the potential difference across a resistor is proportional to the current through the resistor. Current through the resistor. Okay, so that means is, what that means is, if you get the ratio, let's say delta V is proportional to current. This is Ohm's law. All right, so this means the ratio between the potential difference and the current is a constant. The potential difference and the current might change, but the ratio will remain the same. What that means is, if you double the potential difference, the current will double, so the ratio remains the same. If you triple this one, it will triple, so the ratio will always remain the same. Now, this constant is defined to be the resistance of the resistor. It's a property of the resistor. So we call this resistance of the resistor. This ratio is called resistance of the resistor. So this is a property that identifies the resistor. So we're going to use R for this one. Okay, we're going to use R. It's the resistance of the resistor. So Ohm's law can be written as follows. The ratio between potential difference and the current through the resistor is equal to the resistance of the resistor. But this is customarily written as potential difference through resistor equals current times the resistance of the resistor. Okay, so this is a mathematical statement of Ohm's law. Okay, so in this formula, delta V is potential difference across the resistor. Okay, I is current through the resistor, and R is the resistance of the resistor. Okay, now let's look at the unit of resistance. Unit of resistance, or R, resistance. Now, as you can see from this formula, resistance is potential difference divided by current. So this is the unit of potential difference, which is volts, divided by the unit of current, which is amps. Okay, this is defined to be ohms. Okay, and the symbol for ohms is omega. So the unit of resistance is ohms, or we can use the symbol capital omega to represent it. Okay, so Ohm's law states that the potential difference is proportional to the current, and the constant of proportionality between potential difference and current is called resistance of the resistor. Now let's see how we measure the current and the potential difference. Okay, so let's say we have the battery over here. To measure current is measured by a device called ammeter, and the ammeter is put in series in the circuit. Okay, so this is a device for measuring current, and it's called ammeter. Okay, it has to be placed in series in the circuit. So they have to cut the wire and put the ammeter in between. The potential difference is connected in parallel with the resistance, and it's called a voltmeter. Okay, this is a symbol for a voltmeter. It's a device that measures potential difference between 2 points, and it's called a voltmeter. Okay, so remember, an ammeter is put in series in the circuit, while a voltmeter is put in parallel with the resistor, just like this one. All right, so this measures I, this measures delta V, or potential difference. So the main thing is an ammeter has to be put in series. This has to be in series, and this one has to be in parallel with the resistor. In parallel with the resistor. Okay. So example, when a resistor is connected to 6-volt battery, let's say a current of, let's say, 2 amps flow through it. 2 amp flows through it. The question is, calculate its resistance. Calculate its resistance. Okay, so what we have is, we have a resistor connected to a 6-volt battery. That is, the potential difference of the resistor would be 6 volts, and then a current of 2 amps flow through it. Okay, the question is, calculate the resistance of the resistor. So we have Ohm's law, potential difference equals current times resistance, which implies resistance equals potential difference divided by the current, and that is 6 over 2, which gives us 3 ohms, so omega. Okay, all right. Now, resistors usually come in the form of wires, so we're going to look at resistance of a wire. Resistance of a wire. So let's say this is a wire of cross-sectional area A and length L. Now, the greater the length of the wire, the greater the obstacle the charges will experience when they cross the wire. Okay, so the resistance of a wire is proportional to the length of the wire, and the greater the cross-sectional area, the easier it is for the electrons to cross the wire. So the resistance is inversely proportional to the cross-sectional area. Okay, so we have the following proportionalities. Resistance of a wire, resistance of a wire, we have these two relationships, is proportional to the length of the wire. Length, we're going to use L of the wire, and the other relationship is it's inversely proportional. The greater the area, the smaller the resistance, the cross-sectional area, inversely proportional to the cross-sectional area of the wire. Cross-sectional area of the wire. Okay, we're going to use A for cross-sectional area. Okay, so mathematically we're saying is the resistance of the wire, let's say length L, is proportional to the length and inversely proportional to the area. Okay, so this means is the ratio between the resistance of the wire and this expression over here, length divided by cross-sectional area, is a constant, but it doesn't change. All right, this constant is defined to be the resistivity of the material. It's a material constant, that is the same for the same material but different for different materials. For example, copper will have its own resistivity, silver will have its own resistivity, and so on. So for given materials, a constant, but for different materials, it is different. So it is a material constant. It is a material constant, and it's called the resistivity of the material. It is called the resistivity of the material. Okay, and we're going to use the Greek letter rho to represent it. Okay, we're going to use the Greek letter rho represented. So we have the following. So this ratio, the resistance of the wire divided by the ratio of the length of the wire to the cross-sectional area is equal to the resistance of the wire. But this customer written as the resistance of the wire is the resistivity times length divided by cross-sectional area. Okay, so to calculate the resistance of a wire, all you have to do is find this value, maybe from a table in textbook. This resistivity is a constant you can find in tables in textbooks, and then if you know the length and the cross-sectional area of the wire, you can calculate the resistance of the wire. Okay. So let's look at the unit of resistivity. Unit of resistivity. So as you can see from this formula, we have the resistance equals resistivity times length divided by cross-sectional area. This implies resistivity equals resistance times area divided by length. Okay, so the unit of resistance is ohms. The unit of area is meter squared. This is meter, so we just have meter over here, right? So it is ohm times meter. Okay, so this implies that the unit is ohm times meter. Okay, that is meter squared divided by meter is meter. You got ohms for resistance, so the unit of resistivity is ohm meter. All right. Example. Let's say a wire is made up of a material, let's say, whose resistivity is 2 times 10 to the power of -8 ohm meter. Okay, calculate its resistance if it is, let's say, 10 meters long and its cross-sectional radius is, let's say, maybe 4 millimeters. Okay, 4 millimeters. All right, so we're given the resistivity of the material from which it's made of, 10 to the power -8 ohm meter. Okay, now the radius, this is a wire. Okay, so its cross-sectional radius, which is this one over here, is 2 times 10 to the power -3. Okay, the radius is 2 times 10 to the power -3, which is this one over here, right? So the area is pi times radius squared. It's a cross-sectional circular cross-section, so it is pi times 4 times 10 to the power of -3 squared. Okay, squared. All right, and the length we're told is 10 meters. All right, so we can calculate the resistance of resistance equals resistivity times cross-sectional area divided by the length. Okay, no, I'm sorry, length divided by the area. All right, so that is 2 times 10 to the power -8 times the length, which is 10, and then we've got the square of this one be 16 pi times 10 to the power of -6. Okay, so This one is about 50 over here. So from the numbers we have to divide by 5. Let's approximate this number over here by 50. And so we have 2 over 5, which is 0.4. Equals, we have 0.4 from the numbers. And then we have -8, -7, that's 10 to the power of -1, okay? Times 10 to the power of -1. And that, of course, gives us 0.04 ohm will be the resistance of the wire. Okay, now we're going to look how resistivity depends on temperature. So let's look at dependence of resistivity on temperature. All right. So what do we expect to happen when temperature increases? Let's say we have a wire over here. As you know, current is flow of charges. Let's say these charges crossing cross-sectional area. Now what happens when temperature increases? When temperature increases, what's going to happen is the molecules of the material will move very vigorously, vibrate vigorously around their equilibrium position, and so it'll be more and more difficult for the free electrons to cross the wire. So we would expect the resistivity of the material to increase with the increase of temperature. Okay, so this resistivity will depend on 2 factors. Okay, first, it will be proportional to the change in temperature. That is, the greater the change in temperature, the greater the change in resistivity. But also it depends on something else. It depends on the initial resistivity. Okay, so the greater the initial resistivity, the greater the obstacle for the charges to cross the cross sections. So we have the following relationships. We have the following relationship for change of resistivity. Change of resistivity, so that's going to be delta rho, okay, we're talking about change in resistivity, is proportional to change in temperature, is proportional to change of temperature, we're going to do delta T for this one, T for temperature, delta T for change in temperature. It's also proportional to the initial or original resistivity. Proportional to the initial, that's the resistivity before the change, initial resistivity. Okay, we're going to use rho naught to represent the initial resistivity. All right, so let's write this mathematically. We're talking about the change in resistivity. So the change in resistivity is proportional to the change in temperature, but it's also proportional to the initial resistivity. All right, so this means the change in resistivity divided by this product over here should be a constant. Okay, once again, this constant is a material constant, which means it's a constant for a given material but different for different materials. So this one is a material constant, called temperature coefficient of resistivity. It's called temperature coefficient of resistivity. And we're going to use alpha to represent it. Okay, we're going to use alpha to represent temperature coefficient resistivity. So we have the following. Therefore, change in resistivity divided by rho naught and change in temperature equals temperature coefficient of resistivity. But this customer written as the change in resistivity equals the temperature coefficient times initial resistivity times change in temperature. Okay, so that's how change in resistivity is related with change in temperature. This is a constant you can find in tables in textbooks. Right. All right, so this formula is useful for dealing with changes. If you know the change in temperature, you can use this formula to calculate the change in resistivity. But sometimes we're interested in the resistivity at particular temperature. All right, so let's try to modify this problem for these cases. So we can say delta rho is final resistivity with change minus the initial resistivity, and we can say delta T is the final temperature minus the initial temperature. Okay, so substituting this, we have for delta rho resistivity minus initial resistivity equals alpha initial resistivity and then final temperature minus initial resistivity. All right, now we can move this around. Resistivity equals rho naught, which is the other side, plus alpha rho naught, and then change in temperature. All right, then we can factor out this initial resistivity and we have the following formula. So the resistivity corresponding to temperature T is initial resistivity 1 plus alpha T minus T naught. Okay, so if you're interested in the resistivity at a particular temperature, you can use this formula. This will give you resistivity at a certain temperature T. Okay, all right. Now, well, let's look at unit of alpha. Unit of alpha or temperature coefficient. Okay, so from this formula, you see that these two have the same units. Okay, so the unit is basically 1 over change in over unit of temperature. Okay, so this is 1 over degree centigrade, the unit of temperature coefficient of resistivity. You see these two have the same unit, so this goes away. So you just have 1 over degree centigrade for the unit of temperature. Okay. Maybe let's go to the other page. Example. Let's say a certain material has a resistivity of maybe 2 times 10 to the power of negative 8 ohm meter at a temperature of 20 degrees centigrade. Okay. The question is if the temperature coefficient of the material is, let's say, 3 times 10 to the power of negative 3 per degree centigrade. Calculate its resistivity at a temperature of 120 degrees centigrade. Okay, so what we have is our initial temperature is 20 degrees centigrade. Okay, and then temperature is increased to 120 degrees centigrade. All right, and the resistivity at this temperature is 2 times 10 to the power of -8 ohm meter. And we're told the temperature coefficient for resistance for the material is 3 times 10 to the power of -3 per degree centigrade. So the question is to calculate resistivity at 120 degrees centigrade. Okay. So in this case, we're looking for the resistance to the particular temperature, so we can use this formula over here, this one over here. Okay, so we have resistivity equals initial resistivity, and then 1 plus temperature coefficient of resistivity times the change in temperature. Okay, so we have this is 2 times 10 to the power of -8, and then we got 1 plus 3 times 10 to the power of -3, and then we have the change over here, 120 minus 20. Okay, so obviously this is 100 over here, and 100 times 10 to the power -2 would be 10 to the power -1. So this is 2 times 10 to the power -8. You got 1 over here, and then 100 times 10 times 10 to the power -3 is 10 to the power -1, and then we get 0.3 over here. So it is 1.3 times this resistivity. Okay, so that'll be 2.6 times 10 to the power -8 ohm meter. Okay, so its resistance will increase from 2 to 2.6 when temperature changes by 100 degrees centigrade.